Here's another vector problem example. We've got an airplane and wind. Again, the difference here is that you're given the bearing of the plane and the wind, not the traditional angle that we're used to. All right, so we're going to start by converting the bearings of the plane and the wind to an actual angle theta, and then we're going to solve the problem real quick. I'm going to cruise through the rest of the problem quickly, where we're just finding the component form of each vector, adding the vectors together, and then going back and finding the actual speed and direction of the plane after it encounters that wind. All right, so let's look at the plane first. Let's look at the plane, Alaska Airlines plane. The bearing is, if you don't remember, is the bearing is the clockwise rotation from north. So if north is straight up in the air, if north is straight up in the air and the plane is flying at a bearing of 40 degrees, that is 40 degrees clockwise from north. From north. So the actual direction of the vector is just like so, just like that. We'll make it a little bit longer because the plane is traveling pretty fast. And so if we want, let's see here, think of that. Nice. If we want, let's make that the x-axis. Or let's make that, we could say that's, what is that, that's east, I guess, huh? This is theta. This is theta. 90 minus 40 is 50 degrees. Alright, so theta for the plane is equal to 50 degrees. And the magnitude of P, here's P, the plane vector, is its speed, which is 500 miles per hour. Let's do the same thing quickly for, let's see here, for the wind. Here we go. Nice, nice. So here's north, here is east, here's west. The plane has a bearing of 280 degrees. So I'm going to start north and go clockwise, 90, 180, 270, 280, 280. So the plane's vector is in this direction. That's not even, it's probably more like that. 10 degrees is not very much. And it has to be a lot shorter, and it's only traveling 50 miles an hour. So let's go like that. Very small vector. Alright? And we are going to need to calculate that angle. That angle is going to be on theta. It's going to be the actual direction of that vector. Let's see, that's 10 degrees. So theta is going to be equal to 180 minus 10, 170 degrees. Got it. So we just converted both directions from bearings to a direct angle, counterclockwise from the x-axis. 170, and the magnitude of the wind is 50 miles per hour. All right, let's cruise through the rest of this problem. Let's cruise through the rest of the problem. Now that we got the information, we are going to find, let's see, the plane vector on its component form. Give myself a little more room here. Alright. Component form, to make a long story short, you just always take the magnitude times cosine of the angle. That's for the horizontal component. And then the magnitude times sine of the angle. Easy enough, all right? I did that calculation already. Let's see here. That is, the horizontal component is 321.4, and then the vertical component is 383.0. Okay, those are the two components of, just to be clear, those are the components of that vector right there. It's over 322 and up 383. All right, so the wind vector, the components of that little of that little short vector right there are the same formula. All right, the angle times cosine. I'm totally messed that up. I cannot go through the whole video without a mistake. The magnitude times cosine of the angle. The magnitude times sine of the angle. All right, I got that calculation. So that is left or negative 49 on the dot, 49.0, and up 8.7. Awesome. All right, we got our two components. We are ready to rock. All right. Then we're going to combine the vectors to see what the component form of the plane and the wind is. Different color. Let's go green. So we're going to combine them just by adding those two vectors. Piece of cake. So adding the horizontal components together. Let's see here. Looks like it's right. 29. 272. Yeah. 272.4. And then the, well, that's easy. What is that? 391.7. I add the vertical components together. Got it. 391. Yeah, sure. Awesome. All right. And then, from the component form, let's talk about that adding real quick. So really what I just did is I took that little vector and I added it to the end of to the end of the plane vector, and the resultant vector looks like that. That vector represents the actual path and speed of the plane. I mean, that's it right there. Let's make it big and bold. Big, yeah. That's P plus W. Yeah. All right. So we're trying to find the direction of that, the angle of that, and the length of it to help us find the actual speed and path of. Yeah, let's bring that down. Check this out. Because I can copy, paste. Oh yeah. There we go. All right. Let's use that picture to help us out. So the magnitude is going to be the speed of the plane, 272.4 squared. This is Pythagorean theorem. Square root of all that. I'm going to redo that real quick on my calculator because I actually, when I work it out before, I just don't remember. Plus 391.7 squared. Square root 477.1 miles per hour. That really is the length of that of the plane. So of this vector. So that means that the plane was going 500 miles an hour. The wind slowed it down. It's kind of the wind is kind of in the face of the plane. It slows down. It's slowing down that plane. All right. The angle is I just use this formula. Tangent is always equal to y on x. This is the opposite side. This is the adjacent side. So theta is always equal to inverse tangent of y over x. Inverse tangent of y over x is 391.7, 272.4. I've got that one. It is equal to, let's see here, 55.1 degrees. That is that angle. That is that angle. All right. Let's talk about that angle real quick. Oops. 55.1 degrees. Now, because I was given a bearing, I want to find the actual bearing. Clockwise from north. So the actual bearing, I'll call it B. 90 minus 55.1, which is 34.9. There's the bearing. I like it. Direction is speed of the actual plane after it encounters that wind. Awesome.
Awesome. Thanks for listening. Later.